This is lecture 13, number 1. I will deal with chapter section 11.1 and 2 now. And then next lecture will be the 11.3. And then I will finish the remaining chapters until the Sunday. I'm sorry, it will be delayed. I'm sorry. I did not secure the plan of the time. I'm sorry. Okay, the topic of chapter 11 is about control. Okay, now I will begin with the fundamental theory of a control system. Maybe if you have learned control system technology undergraduate student, maybe it can be skipped. Anyway, I will read and I will summary the elementary level of control. In tasks such as the writing on chalkboard. Okay, let's assume that the robot is writing on the chalkboard or blackboard using the chalk. At that time, the chalk direction should be controlled in terms of force, is right? Because chalkboard will be the environment to constrain the movement of the robot. On the other hand, the writing will be performed or conducted in the plane of the chalkboard or blackboard. Like this, the control objective will be the two kinds of things, force and motion. Okay, on the other hand, the job of robot control is to convert task specification to force and torque applied to be applied actuator. Okay. Anyway, the robot control will transform the task specification to the force and torque. Okay, now in chapter 11 deals with 4 kinds of control theory. The first one is motion control. This is the 11.3. Force control 3 and 4, and 5 and 6 and 7. Like this, motion control, force control, hybrid motion force control, impedance control. 4 topics will be covered in this chapter 11. Okay, the robot, you should mark in mind, the robot cannot independently control the motion and force in the same direction. It means if the robot imposes the motion, then environment will determine the force. So, on the other hand, the robot imposes the force, then environment will determine the motion. It is similar with the writing on the chalkboard. Okay, the environment and the robot will perform independently. Okay. Once we have chosen a control goal consistent with the task and environment, we can use feedback control to achieve it. Okay, just read it. Okay, let me summarize. Let me explain the control system. Okay, the first one, the desired behavior is given by the user or operator. The behavior includes motion and force. Okay, and then the controller will transform or convert the error to the low power control. Maybe it can be used in the form of voltage, and then in many cases, amplifier is used to provide a big pulse. So amplifier will generate high level pulse control. It can be current And then the actuator will conduct the motion or generate pulse according to the command of amplifier. At that time, the current, electric current, will be feedback to the amplifier. So this loop will perform the electric current control very fast way. And then the actuator will provide the motion or pulse or torque to the dynamics of robot system and the environment. And we are using the sensor to capture or understand what happens in the robot in the environment. So the motion and the pulse will be captured or measured, and then it will be feedback to the control. This is the POMA procedure of the control system. So in here, we will deal with control theory occupied here. Okay, sensor. Sensor is very important. Actually, the robot making use of the many kinds of sensor. Okay, potentiometer. Potentiometer looks like the variable resistance. Okay, potentiometer encoder. Encoder is the digital device to measure the angle. Resolver, analog device for joint position and angle sensing. The typical sensor will be the encoder. Okay. The tachometer is used for joint velocity. Nowadays, the tachometer is not powerful, or it is not used actively. But long time ago, when I was a PhD student, tachometer is very useful. Okay, and then joint pulse torque sensor. It's a one-dimensional device. The joint pulse torque sensor is equipped in the actuator and harmonic device. Okay, so nowadays many kinds of well-known robot system has the joint torque sensor. Okay. Many cases, the is actually the 6-axis pulse torque sensor at the least between the end of the arm and the end effector. Okay, this is the more formal. In my case, encoder and the 6-axis pulse torque sensor I used to perform the control, pulse control and the position control. Okay, the control samples the sensor data and update each control signal. So the sample is to obtain the measurement information, and update implies providing the control action to the amplifier. Okay. In this many cases, it is performed at the rate of 100 to a few thousand of hertz. Okay, the inner loop, the amplifier and actuator will use the electric PI control, electric current PI control. Maybe it is very fast, such as over the 20,000 hertz. Okay, so on the other hand, the outer loop will be performed such as a few thousand or a few hundred hertz. Okay, in here we will assume that sampling time is almost 0. Okay, and control will be implemented in the digital device, but we will assume that control is continuous time form. Okay, to avoid the early aging effect. Okay, real robot systems are subject to flexibility. Many flexibility is caused by the harmonic device and vibration. Maybe the source will be the same in the joint and the link. In many cases, backlash exists in the gear device, and then actuators as the performance limitation. So actual saturation limit should be considered, and limited resolution of a sensor. Okay, this kind of issue lays significant problem in design and control. Okay, next topic. Next section is about the aerodynamics. Okay. Consider the controlled dynamics of a single joint. Let's define joint error as a desired angle minus actual angle. Okay. This joint error will be denoted by the theta E as a function of time. Okay. The differential equation governing the evolution of joint error of the controlled system is called as aerodynamics. Okay. So after defining the error, and then we should derive the differential equation in terms of the error, then we will call it aerodynamics. The purpose of the feedback control is to create aerodynamics such that error goes to zero according as time goes to infinity. Okay, this kind of phenomenon is called as asymptotic property. Anyway, we want to obtain the asymptotic property, asymptotic stability. Okay, it means error should go zero according as time goes to infinity. Okay, error response. Response is the output of the aerodynamics. Okay, this figure shows the typical response of the error. Okay, it must be the error initial condition, and then after several vibrations, it will arrive at the steady state. In order to separate the transient and the separate region, we will define the settling time. In this book, 2% settling time is used. Before then, transient response. After then, steady state response. Okay. So the overshoot is defined from the equilibrium point to the maximum or minimum. Okay. The first peak will be used to obtain the maximum overshoot. Okay. And, okay, let me read it. A common way to test how well control works is to specify non-zero initial condition error, such as 1 is given, then we will examine the response of the aerodynamics. And we will see how quickly, how completely controller reduce initial error. This error should be quickly removed. This error should be completely removed without any remaining errors. That will be the specification of error response. As mentioned before, response is composed of transient response and steady state response. Okay, steady state response will be described using the steady state error, the remaining error here. This is the remaining error, is right? It should be removed or maintained in as small as possible. Okay, the transient response is characterized two kinds of things: overshoot and 2% settling time. Okay, it will describe it later. Okay, using the first order dynamics. Okay, the 2%, the error, the first time to satisfy this inequality. This time is called as 2% settling time. Okay. Okay. Good error response is characterized no steady state error, no overshoot, and very short, very fast response time. 2% settling time should be short. Okay, linear aerodynamics. Actually, this book is covered by many linear theory, because linear theory is very well developed, but nonlinear theory is still being challenging issues. Consider aerodynamics described by linear ordinary differential equation of the form. Okay, this is the very formal. The AP theta EP parenthesis implies piece order differentiation. Okay, P minus 1 parenthesis implies P minus 1 order differential equation. Okay, the first order differential equation, this is the just variable. Okay, so in total, piece order differential equation is given. Okay, here the input part is given by the 0. We will call it homogeneous equation. Okay, this is non-zero. Maybe the sine, cosine, or polynomial function can be given here or exponential. At that time, it is called as non-homogeneous. Okay. In here, so we will deal with only the homogeneous linear aerodynamics. So this will be assumed to be 0. Okay, so the remaining P minus P equation can be moved to here, like this, and then we will divide both sides with the AP. So it is the first coefficient. Like this, we can define the new coefficient, okay, such as the prime. It is a prime P minus 1, a1 prime, a0 prime. Okay, and then we will define the state variable. Actually, this is the piece order differential equation, but in many cases, the nth order differential equation can be changed into the n coupled. In here is the p coupled first order differential equation by using the state vector. So the variable theta e will be defined as x1. The first order derivative of theta e is defined by the x2. Maybe the second derivative, 2 times derivative, x3. Like this, xp can be defined using the p minus 1 order differentiation. Okay, and then take time derivative. Every state vector, x1 dot will be the x2, x2 dot will be the x3. Like this, we can assume the remaining variable. The xp dot is equal to this equation, so we will write down like this. It's not difficult. It's a typical way to derive the first order differential equation using the n vector. Okay, so x can be the column vector from x1 to the xp. Okay, so x1 dot will be the x2, is it right? x2 dot will be the x3. Like this, off diagonal term will be the 1. Okay, and then the the last row will be the x1 dot, x1, x2, x3, xp minus 1 will be multiplied. So we have this kind of a system matrix A. Okay, from here, maybe we know that x dot is AX. A is in this case, A is a scalar. At that time, we can derive the solution. Maybe you know that dx dt ax. Let's remove the x dx a dt and then take a time derivative. Okay, here ln x x0 xt at. Okay, the x ln xt minus ln x0. It implies ln x0 over xt. equal to 80. Let's take the exponential function e2 x0 xt, okay, ln, and then e2 at. Exponential to ln is the identity, so xt is given x0 e2 at. Like this, we know that how to obtain the differential equation in the case of the first order. Okay, it's not difficult. When you are second years, we have learned it, the engineering mathematics. You should be good at the ordinary differential equation, how to solve it. Okay, so it must be the xt. Using the initial condition, e to at will be given. Like this, we can derive the solution of the first order differential equation. Okay, p vector, the p coupled first order differential equation is given by the A matrix. The solution is very similar. Okay, xt is given by e to at matrix exponential and the first initial condition vector. Okay, it is called as matrix exponential. Okay, this is exponential function. Okay, in order to make the state to be conversed, the A should be negative. In the case of the matrix, the eigenvalue of the A will be the negative. So negative real part should be contained in this matrix A. Okay, so the vector solution xt tends to 0 vector when A is negative definite. It means all eigenvalue have the negative real component. Okay, and then we will check the stability again. Last stability criterion. Okay, the eigenvalue of the A is given by the root of the characteristic polynomial. The characteristic equation is obtained using the determinant Si minus A. Okay, here's it's not difficult from Si minus A determinant, but the result will be obtained like this. Okay, and then the last stability criterion suggests two kinds of things. First one is a necessary condition. The remaining one will be the sufficient condition. Okay, the necessary condition will be all the coefficients should have the same sign. In here, it must be the monic polynomial because the highest order coefficient is the 1. It is called as monic polynomial. Okay, here's the first order coefficient is the 1 as a positive, so remaining coefficient should be positive. So one of them is negative. It has the unstable response. Okay. The sufficient condition will be the last table. Maybe you are good at this concept. Anyway, the XP order is given by the highest order, and skip one more p minus 2 order coefficient, one more, and then p minus 1 order, the highest one, and then jumping to, then we have the p minus 3, p minus 5. Okay, here the next ps minus 2, we should calculate this term. p minus 1 should be denominator, and the numerator will be the times of these parameters minus this one. So actually the result will be p minus 2 minus p minus 1, p minus 3 over p minus 1. It is the new first column, first law of SP minus 2 order polynomial. And the second one will be this part times a p minus 1 times a p minus 4 minus 1 times a p minus 5 over a p minus 1. So it can be obtained as a result a p minus 4 minus a p minus 5 over a p minus 1. Like this, we can write down all the last table. And then we will check the first column. This one. This column should have same direction, same sign. So first one is 1. Every term should be positive. That is the necessary condition to have a stable response. Okay, so from here, it should be positive. Okay, maybe you have the next one, then this is also should be positive. This is derived. This procedure is derived from the laws at the end of 19th. If each root of classification negative real part, then error dynamics will be stable. Okay, because all the eigenvalue will be the negative. If any of the roots have the positive real part, let's assume that the p eigenvalues exist. Here's one of them just have positive. At that time, response will be the unstable. Okay, is it right? So any of the roots have the positive real component, error dynamics will be unstable. Okay. Okay, let's assume that we have the mass spring damper. Okay, then we will apply the Newton's law to obtain the equation motion. Okay, the inertia is given by the m. Okay, okay, the displacement is denoted by the theta e to make the equation consistent. Okay, so m theta e 2 dot is the inertial force of this system, and inertial force should be equal to some of the external force. In here, we have the 3 external force. F is given by the usual, and the minus k theta e minus b theta e 2 dot to against motion. So it is the external force. Okay, then by moving 2 terms from the right to the left, we have this second order differential equation. Okay, it can be checked. The stability can be checked by using the Rouse stability criterion. It's very simple, so let me write down again. S2 is M and K. S1 is P and 0. S0 will be the K minus, okay, actually the M times 0, so K, it's okay. The M should be positive, B should be positive, K should be positive. So all the coefficient is positive. The solution, theta e 2 dot, will converge to zeros without when the external force does not exist. Okay, in here, let's assume that mass m approaches to 0. Mass is very small. Then we have first order differential equation. Okay. Okay, I will review the first order first and then second. Okay, here, according to the, okay, let me assume that the external force is 0. Then let's divide the first differential equation with the b. Then we have these terms. We will write down these terms in terms of time constant. I think that you are good at the concept of time constant. Okay, let's assume that time constant is defined by b over k. Okay, then the time constant will exist here. Okay, and then maybe you are good at the theta e t, and then Laplace transform will be defined es, okay, to make the notation easy. And then theta e dot, the differentiation of theta e will be SES minus initial condition. Is it right? Maybe one more, theta e 2 dot t will be S square ES minus theta E 0 S minus theta E dot 0. Two initial conditions are given, should be utilized to derive the ordinary differential equation in terms of the S. Okay, anyway, the first differentiation will be given by like this, and the second one. Okay, let's collect ES. Then we have this equation. Maybe the inverse Laplace transform 1 over S plus A. What is that? E2 minus AT. So it is corresponding to the A. So we have E2 minus T over tau theta E. Okay? It will be the solution. Okay, so the time constant t at tau is the time at which the first order exponential decay has decayed to the approximately 37% of its initial condition. So the time constant, okay, let me draw again like this. This part will be the 37%, 0.32, if the initial condition given by 1. And this is the initial the first time constant. How about the second? 2 times of this one. I remember that this is the 30%, 3 tau. It is corresponding to the 5%. The post tau, 4 times tau, will be the 1.8. Okay, let me write down here. Okay, tau, the error will remain as a 37%. 2 tau, 13% approximately. 3 tau, 5%. 4 tau, 1.8%, almost 2%. 5 tau is corresponding to the 1%. Actually, the 0 point, I'm not sure. It is 4.6 tau is corresponding to 1%. Okay. Anyway, it's very easy to remember. 37, 13, 5, 2, and 1. Approximately, it is very useful. Okay, the steady state error will be zeros. Okay, is it right? Because this equation goes to 0 according as time goes to infinity. There is no overshoot. There is no overshoot in the first order differential equation. Okay, and 2% settling time. Okay, I already derived it. Okay, let's assume 2%. The initial condition is the 1. This is a 0.02. So it is 0.02. And E2 minus T over tau. Okay, let's take the natural logarithm between both. Then ln 0.02 minus T over tau. It will be equal to T as a 3.91 tau. So it is very similar. It will be assigned to the 4 time tau. So okay, in here we will use 4 time tau is corresponding to 2% error. Okay. Okay, the response gets faster as the spring constant increase or damping constant decrease. Okay, is it right? Because it determines the time constant of post differential equation. Okay, the second order aerodynamics. Maybe you are good at this equation after assigning S0. Okay, and then we will divide every terms using the m. Then we have this equation. In here, this part will be the 2 zeta omega n, and this one will be the omega n squared. We have two equations and two variables, so it can be easily obtained. Omega will be square root k over m. Zeta will be b over 2 square root km. Okay? Omega n is called as natural frequency of the system, and the zeta is called as damping ratio. Okay, so from now on, instead of first equation, we will use the second equation, because this is the prototype or standard form of second order differential equation. Okay, we will define the state vector, two state vector x1 as an error, x2 error dot. So it's not difficult to obtain system matrix A, then like this. Okay, by taking a time derivative both sides, then we will get the A matrix. And then the characteristic equation will be determined by the determinant of Si minus A. So we have this equation. Each root can be obtained using the quadratic formula. So we have a first quadratic formula and the second quadratic formula. If zeta is larger than 1, this is the slow. This is a small, this is near to the origin compared to the S2, because it will be the negative minus negative will be the big negative value. So if you consider the sigma axis, real number axis, and the emission axis, j omega, and S1 will be near to the origin, okay? And S2 is far from origin compared to the S1, okay? Do you remember that? We will say that the near origin near eigenvalue, the root will be called as a slow one, okay? Because the time constant is determined by this value. Okay, the time constant will be the very large compared to the S2. Okay. Okay, actually according to the value of the zeta, this equation have the three types of solution. Okay, S1, S2, the roots are real and unequal. In the case of the zeta larger than 1, the second one real and equal, and the complex conjugate. We will deal with the three kinds of system matrix from now on. Okay, first, from here, we have the two. The first case is about we have two real and unequal. The second case, real and equal. The repeated pole, repeated root, repeated eigenvalue. The three terminology are same each other, and then complex conjugate. Okay. The overdamped case, I'm sorry, it is the S subscript 1 or 2. It is typo. Okay, S1 or 2, and the real and the distinct, and the solution will be the two complex exponential. Okay, it's not difficult. Maybe you are good at if you are good at the Laplace transform, then it is easy, because S minus S1 over C1 plus S1 minus S2 over, like this. The previous equation can be decomposed using the partial fraction method. Okay, zeta e as take a time derivative, take inverse Laplace transform, zeta e t, the c1 e2 s1 t, c2 e2 s2 t. So we have this equation. Okay, so we have two kinds of time constant. Okay, the t1 as a minus 1 over s1 and minus 1 over s2. As mentioned before, the origin near the point will be the slow one. Okay, it will determine the system response of second order. And then the C1 and the C2 can be obtained using the initial condition. So if you apply the one initial condition and the zero velocity initial condition, then you can get the C1 and C2, which is not difficult. Okay, the second case is critical damped. S1 and S2 can be obtained minus omega n. Okay, the equal and the real and the repeated values. Solution will be the C1 plus C2t and E2 minus omega n t. The repeated pole can be replaced, can be transformed into the original value times t. I'd like to recommend you to check the Laplace table. It's not difficult. Okay, the t should be multiplied to obtain the repeated pole case. Okay, time constant is just 1 as a 1 over omega n. Okay, and then the error response can be obtained by applying the two initial conditions. Then we have the C1 and the C2. Okay. Okay, more difficult case will be the undamped zeta as given by less than 1. The roots are complex conjugate. Maybe you're good at this one. Omega n will be the omega d will be omega n times 1 minus zeta square. It is omega d will be called as damped natural frequency. According to the damping ratio, this value will vary. Okay, solution will be given by the E2 minus zeta omega n t. It is called as envelope. It determines the shape of the overall shape of a response, and sine and cosine will be given. Okay, C1, C2 is also given by initial from the initial condition. And in here, the zeta omega n, inverse of zeta omega n will be equal to time constant. So in the overdamped case, we will choose the slow eigenvalue as a time constant. And then the critical damped and underdamped case, the time constant is given by 1. In the case of the critical damped, omega time constant will be given by 1 over omega n. On the other hand, under the damped case, 1 over zeta omega n. So if you have the small zeta value, the time constant will be big values. Okay, so it is dependent on the omega n and zeta. Let me show you the last phase of certain lecture 1. Okay, this figure shows the relationship between the root location such as the type 1, type 2, case 1, case 2, case 3. Okay, the property of the transient response. Okay, here roots further to the left, such as this is given by the eigenvalue of the overdamped system. Okay, one more. If you given by the like this, compared to the left case, is fast. Okay, roots further to the left in the complex plane, corresponding to the short settling time. It means past response. This is the past. Okay, this is the slow. Okay, root further away from the real axis. Okay, like this. If you have the complex eigenvalue like this, compared to this one. Okay, the root further away from the real axis. Okay, this one and this one corresponds to the great overshoot and oscillation. It means the response will be a little bit fast compared to this one, but this angle is corresponding to the damping. Damping is smaller than the previous one. So the real axis, the root further away from the real axis, it will give you the big overshoot and the big oscillation. Okay. In the case of the underdamped underdamped response, there is a peak. Okay. In the underdamped case, the peak exists. Okay, the peak can be obtained theta et by taking a time derivative should be given 0. This time will be dp, peak time. Peak time, after obtaining this derivative, we can get the dp as a pi over omega d. Okay, if you apply the dp to the theta e equation, then the result is very simple. It's just given by function of zeta. Okay, minus e2 minus zeta phi 1 over 1 minus zeta square. Okay, the maximum overshoot is only function of zeta. Okay, as you can see in this equation. And okay, the zeta is given by 0.1. Maybe though you have the 73% overshoot. Okay, zeta is given by 0.5. The 60% overshoot will appear in the response. 0.8, 1.5. Very small sized overshoot exists. Okay. Okay, the next issue will be the 11.3, the motion control